welcome to our session on elimination reactions. Now, an elimination reaction in organic chemistry is a reaction in which two adjacent atoms or groups of atoms on adjacent carbon atoms are removed from a molecule and a double bond forms. So, in other words, an elimination reaction is the reverse of an addition reaction. In an addition reaction, we went from unsaturated to saturated. Now we're going to go from saturated to unsaturated. So what we need to remember is we're going to take atoms off. Those atoms will form a new bond and we will form a double bond, okay? And they will always be from adjacent carbon atoms. They can't be from the same carbon atom. All right. Let's go to the first one. So the first ones we're going to look at is D. D means, taking it off, hydrohalogenation. So in other words, we're going to remove a hydrogen and we're going to remove a halogen. Now, in order for this to happen in general, we're going to have to start with a haloalkane. Otherwise, where does the halogen come from? We need a strong base. We're actually going to stick to sodium hydroxide or potassium hydroxide. And that means we're going to end up with an alkene, a salt, and water. Okay, the salt will come from the base, and of course the water is from the OH. So, reaction conditions, very, very, very important. We have to have a concentrated strong base. That's actually quite important. If we don't state that it's concentrated, it is a problem, because if it's not concentrated, it could be a substitution reaction instead. We then have our base, which is sodium hydroxide, potassium hydroxide, doesn't matter, dissolved in ethanol, and then we heat it under reflux. This whole issue of under reflux, what that is for is to mean that we can make it a high heat. It has to be heated quite strongly. It's got to be very hot for this reaction to happen. Let's look at an example. So here we have, they want us to do the dehydrohalogenation of CH2ClCH2Cl. First thing we have to do is we need to draw it. Okay, so we have CH2. There's the CH2. We have Cl attached to it. Then we have a CH2 and a Cl. Now, we're going to add it to a base. What I need you to take note of here is I'm not going to show the bonds between the sodium, the oxygen, and the hydrogen because it's ionic. Okay, I only show covalent bonds. This means it's dehydrohalogenation. So I'm going to remove one chlorine and I'm going to remove one hydrogen. It makes no difference which ones we remove, as long as they're from adjacent ones, because it'll give me the same product. That means each carbon loses an atom, so now it needs to form a double bond. We're going to be left with a hydrogen, a chlorine, a hydrogen, and a hydrogen. Okay, so we go from having 1,2-dichloroethane and we end up with chloroethene. Okay, don't forget we need heat. Very, very, very important. Nothing difficult about this one as long as we do them from two adjacent carbons. What happens though when it's not as simple as that? So just like we had the Markovnikov rule in the addition, what happens when there's a choice? So here we have, let's draw this so that it's going to come out looking properly. So we have CH2, all right, Br, then we have a CH and a Br, then we have a CH3. We're going to add I forgot something out in the last one, so there's my, oh boy, this isn't good enough. So if we go back here, I do apologize, the sodium will bond to the chlorine that was taken off, and we're going to have H2O. Don't forget the salt and water. I get very excited about what I'm doing and then I forget things. Alright, so we're going to add this one to sodium hydroxide. Right, now we've got to make a decision. We have two bromines, so either this bromine's going to come off or that bromine's going to come off. How do we make a decision? Well, this is the reverse of Markovnikov's rule. Remember, Markovnikov's rule said the hydrogen is going to go to the carbon with the most hydrogen bonds. This is the opposite. Hydrogen wants to stay where it is. All right, so we're going to be removing a hydrogen and we're going to be removing a bromine. But I will not be removing a hydrogen from this carbon because there's already two. Those hydrogens are they want to stay there. It's that bromine that's going to come off and that hydrogen. In other words, this is what I'm saying to you. I know this first over here, that carbon can't lose any. We need to create a double bond. I'm not needing to decide where does the bromine stay. Well, the bromine's going to stay on the carbon that had the least number of hydrogens in the first place. So the bromine is going to stay here. Up or down doesn't make a difference. And the hydrogens are going to stay there because now there's still lots of hydrogen friends there. Okay, it then means that I'm going to end up with my salt, which in this case will be sodium bromide. I don't show the bonds. And I'm going to be left with water. Okay, so if more than one elimination product is possible, the major product is the one where the atom is lost from the adjacent carbon with the least number of hydrogen atoms, which is why the hydrogen came off the carbon, the middle carbon, this one. Okay, that one comes with time. We need to look at it. It's the reverse of the Markovnikov rule. All right, great. What if I wanted dehydration? Now, hydration in addition meant we added water. So now I'm going to remove water. How do I do that? Well, I take an alcohol and I need to use concentrated sulfuric acid as a catalyst. Please, sulfuric acid is not only a catalyst, it is a dehydrating agent. It can remove water and we need to heat it. So, starting with ethanol. Okay, just giving us a nice easy one. Ethanol, it doesn't matter where the OH is. We know that what's going to happen, we're using this as a dehydrating agent. It's not reacting. Okay, it's not a reactant. It's a catalyst that goes on top of the arrow. So this OH is going to come off and one of the hydrogens adjacent to it is going to come off. So that means I'm going to end up with ethene and water. Okay, straightforward, nothing difficult about that one. What happens though when we have options again? Always we do the major product. Okay, so now they've got butane 2-ol, so we have a secondary alcohol. All right, so butane 2-ol. Here's, I'm going to put the OH actually at the bottom. There's my butane 2-ol. So now we've got some decisions to make. Oh, that's not even butane 2-ol. That is propane 2-ol. There we go. There we go. So we're going to add sulfuric acid to it. I know one of my compounds is going to be water. I'm just going to put that there because it's going to make life easier. So I know I'm going to be taking that OH off. We now have to make a decision. Do we take a hydrogen off this first carbon or off the third carbon? The rule that we just looked at over here said that if there's a possibility, the major product is the one where the atom is lost from the adjacent carbon bonded to the least number of hydrogens. So we look back here and we go, well, the first carbon over here has 1, 2, 3 friends. This one only has 2 friends. That one's got least number. So I'm going to take a hydrogen from that one. So those things are going to bond together, which means my double bond now gets created between the second and the third carbon. So it becomes butane 2-ene. Okay, I don't know why I was doing that off at an angle because it won't happen. So this will leave there. Oopsie daisy. There we go. And nice and simple, straightforward. So that's my second product. Okay, now, next one. Write an equation for the dehydration of pentan 3-ol. Show the reaction using structural formulae. Name the products that are formed. Alright, so first thing says the reaction, write the reaction for the dehydration of pentan. Pentan being 5. It's pentan 3-ol, so it's H11OH. General formula, I use CnH2n plus 1 OH to get the formula for that. It's dehydration, so I know I'm going to add H2SO4. It's going to form pentene and water. Okay, but they want structural as well. So let's see if I write really neatly, if I can actually get this all in one. 1, 2, 3, 4, 5. Pentan 3-ol, so my OH goes on the 3rd carbon. Here we go. Draw it all nice and neatly. Okay. H2SO4. So, we know 1, 2, 3, 4, 5. We have to make a decision. Is this going to take off this hydrogen or this hydrogen? Well, actually, it makes no difference whatsoever. And that's something you can do for yourself. I'm going to take off the one on the left. So in other words, I'm going to put my double bond there. So it becomes pentene. If you take it off on the other side, it's still pentene. Draw it out for yourself. You'll see it's the same thing. So we get this. One up, one down. Doesn't matter if they're both up, both down. Makes no difference whatsoever. Plus H2. Oh, no, we need to draw that one out. Sorry. Let's just take that away. Plus H2O. So what does that mean is we end up with pent 2-ene and water. Okay, they said name the products. Both things. All right. So, why are elimination reactions important? It's for cracking. Now, cracking is the process where we take long hydrocarbon chains, because remember, molecules can be long. They can have millions of carbons in them, and we break them down into smaller, shorter, more useful products. It's how we get petrol. Okay, crude oil, which we mine and we get off out of the sea and out of the ground, is a very, very, very long chain, which is quite unuseful. It's not useful to us. We can't do anything with it. So we need to break it up, and there's lots of processes. We're going to do this very simply. We have 2 different types. Please, you must know the conditions. We have thermal cracking, which means we do it under very high temperatures and pressures. 450 to 750 degrees, about 70 atmospheres, very expensive, very dangerous. Then we have catalytic cracking, which uses a catalyst like platinum, but then we can do it at lower temperatures and lower pressures, which means it's not as expensive. But what does cracking do? I'm going to give you an example. Now, there's lots of ways cracking can happen, but if we look at the cracking of butane. Now, butane is very simply what is 4 carbon atoms, right? So 1, 2, 3, 4. That's butane in a nutshell. Now, whether I do thermal cracking or catalytic cracking, it actually makes no difference. What we're going to do is I can break this up. Now, by cracking, I can split this up. I break the molecule up. I don't add anything else. I'm taking stuff out. That's why it's an elimination reaction. But I'm going to create double bonds. So the first thing is if I just took off 1 carbon, in other words, created methane, I'm now left with 3. All right, those 3 have to create ethene. That's one option. The other option, okay, so that's one option of how this could have been broken up. My other option is instead of doing a molecule with 1 atom and a molecule with 2 atoms, I could have created two molecules with two atoms. In other words, so this is the other option, is I could have done this. Created two ethene atoms. All right. But if you look at this, you go, well, hang on, wait, there's a problem here. 1, 2, 3, 4. There's only 8 hydrogens. The original had 10. That also means that then I have hydrogen gas that comes off as well. What the products are depends on the way it's cracked. Okay? Here, when they ask you questions, they have to tell you at least one of the products so you understand what you get for the rest of it. All right? Not a big thing. Cracking is simply taking long molecules, either through thermal cracking or catalytic cracking, and breaking it up into smaller particles, smaller molecules, one of which will have to be unsaturated. All right, they will have to be double bonds in order to make them more useful.